This lesson is about chi-square testing. Chi-square testing is an idea, a test that we can use when we have qualitative data. We want to look for a relationship. Scatter plots are fantastic, but you need numbers for them before you can make or do a regression analysis. Chi-square testing is what we do when we don't have numbers, when we have words. Or we have some numbers, but we have to group them into intervals, high, low, medium, things like that. What a chi-squared test does is it examines the difference between what you've observed and what you would expect to observe. Okay, so we're going to do an experiment, we're going to organize our data, we're going to see what we got, and we're going to compare that to what we theoretically would expect to get. If there's a big difference between those, well, something's happening. If there isn't, well, then nothing's happening. And that's what the chi-square test would do for us. The symbol for chi-square is this fancy X thing here. Okay, so we're going to have to make some tables. So, parts and pieces setting up this test. The first thing is we have some hypotheses. What are we actually testing? And you need to write these down every time to figure out what you're doing. And we call them the null hypothesis and the alternative hypothesis. The null hypothesis, H0, is whatever your variables are, and we'll show some examples in a second, and we want to say they're independent. They have no relationship between each other. The alternative is they are not independent. There is some relationship. I don't know what the relationship is, I just know that there exists a relationship. Yeah, so that's the first thing you write down, your hypotheses that you want to test. The next thing we're going to do is we're going to take our observed values, which is the table we actually find and organized, and create an expected value. An expected value is a proportion. A proportion based on how many things there were altogether out of the total. So we're going to use this little formula here. Row divided by total times column. And I'll explain when we look at an example. Following that, we're going to find the chi-squared value. The chi-squared value is this fancy equation, and I'll come back to that when we get to the example and explain the parts and pieces. It won't make sense quite yet. So here's our first example, and I would print this off the website. It's a handout. We can do it together so you can see where these numbers are coming from. So 100 students. There seemed to be a difference between genders in their choices of favorite car color. The results are given in the table below. So looking at this, it looks like males prefer blue and green and females preferred red. Just at first glance, that's what I'm looking at. So it seems like there's a difference between genders. We're going to test that out. So we're going to figure out our null hypothesis. Genders and color choice, those are my variables, are independent. They have no relationship to one another. That's what I'm thinking. Or gender and color choice are not independent. There is some sort of relationship there. Again, I'm not trying to figure out what the relationship is, just that there exists one. Okay, our expected table, part B. As we said earlier, to find an expected table, we're going to find proportions. Our row divided by the total times the column. Okay, so we're going to make the exact same table we had up here, blue, red, green, male, female, but we're going to base what we'd expect to see based on proportions. Okay, so blue, red, green, male, female, same table. Now, of the total, 60 were males. So I would expect that, theoretically, 60%, 60 out of 100, of the people who chose blue cars would be male. So I'm going to times this by 33, and that's my proportion of people who should be blue. That's 19.8. Okay? 60% of the males should be red car people. There was 32 reds. Okay, and that comes out to 19.2. I would expect 60% of the green. How many greens were there? There were 35. And that comes out to 21. So theoretically, if 60% of the people surveyed were male, then 60% of the people who chose each color should be male. Similarly, theoretically, 40% of them were female. Of the 33, should come out to 13.2. 40% of the red were female, should come out to 12.8. And 40% were female of the 35. That comes out to 14. This is my expected table. Based on proportions, this is what I would expect to find of each of the color choices. Now, obviously, the original table we saw and what we would expect to see are different. The question we have to ask ourselves is, are they a lot different or just a little bit different? That's where our chi-squared value is going to calculate for us. So this is that formula I said I'd come back to. So chi-squared, what you're going to do is take the difference between observed, that's FO, observed, what you actually saw, and what you would expect to see. You're going to subtract them and square them to make it positive, so they're all positive numbers, and then divide by the expected value. And you're going to do that for each part of the table. And that's why we have this big summation thing here. So let's give it a try. The first thing we observed was 24. First thing we expected was 19.8. So I'm going to do 24 minus 19.8 squared over 19.8. That would be male and red. And then we'll do the next one. Male and blue. Male red was 8. Okay, so plus, but I only expected, or I did expect 19.2. Squared 19.2 plus green. We expect 28, we saw 28, we expect 21. And we do the female ones. Female in red, 9 and 13.2. Around the room, so for the next row, okay? And then we expect 24, saw 24, expect 12.8. And the last one, we saw 7, but we expected 14. And there's our expected values. Now, we've got to take our calculator out, subtract them, square them, divide them, add them. And the numbers we should get are, for the first one, 0.891 plus 6.53. There was a big difference in those two. Plus 2.33, 1.34, 0.275, and 3.5. Again, a big difference in that last one. Add them all up, and you should get approximately 14.866. There's my chi-squared value. That tells me how much difference I had on average between each of the expected values and the observed values. Now the question we have to ask ourselves is, for the rest of the test, is that a big difference or not? Is that enough difference to say, hey, there's something going on here? So an idea, there should always be some variability between a theoretical model and a practical experiment. You flip a coin 10 times, you won't get 5 heads and 5 tails most of the time, even though theoretically you should expect that. Okay, so we did this experiment. We're not going to get exactly 60% of males liking each of the colors. There's going to be some difference. But is it a large enough difference to indicate a relationship? So the rest of the test has a few more parts. What we have to do is we have to figure out, first of all, our degrees of freedom. How much choice was there actually? And we can do that by taking the number of rows minus 1 and the number of columns minus 1. Don't include any totals or titles. Those aren't data choices. Those are just things we use to help us solve the test. The next thing we're going to look at is, what's our level of significance? How much variability or error are you willing to accept? Okay. Are you willing to accept 1% error? Do you want to be 99% sure? 5% error, 95% sure? Well, it kind of depends. I'd say our standard, we usually go with 5% error. We're pretty sure. I'm 95% confident. Using the degrees of freedom, in your chosen level of significance, we're going to have to find a critical value from this table. This table, and it's actually a much bigger table, I'll just give you part of it, shows how much how much variability is enough to suggest there's a relationship. Okay, this table makes this graph right here. Our chi-squared value that we calculate, we want to know, is it in this section below the critical value, or is it in this section above the critical value? Because if it's down here, well, there's some differences, but it's not enough to suggest a relationship. But if it gets beyond the critical value, there is enough to say that. Okay, so the last part here, if our chi-squared value is less than the critical value, we're just saying, okay, they're independent. There's nothing going on. But if we manage to get past that critical number, past that, oh, there's something going on here, then we should reject HO and say there's something going on. So we're going to try finishing off this test, okay? Our degrees of freedom, DF. How many rows did we have? Well, it was male or female, so 2 choices. But really, it was only 1 choice. Because if you didn't say male, then it automatically put you in the female category. It wasn't a choice, it was slotted there automatically. How many columns do we have? Red, blue, green. So 3 of them. But if you didn't pick red, then you either pick blue or green. So you really only had 2 choices. So how many degrees of freedom were there? Really only 2. Okay. We're going to test this at 5%. Okay, so we're going to find our critical value. Call it CV. So 2 degrees of freedom. Degrees of freedom are down the side here. So I'm looking at 2. I want to be 95% confident, 5% error. So that's this column. Here's my critical value, 5.991. I'm going to compare my chi-squared number from back here. We said it was 14.8 to this number. Ooh, chi-squared, 14.8. Well, I would say since chi-squared is much greater than the critical value, that's a big number. We're way beyond that. Way beyond that critical value. We're going to have to reject HO. There's something strange going on here. Okay. We're going to say there is evidence to suggest that gender and color choice, oops, what's that letter there, and color choice are not independent. Okay, we're taking H1. There's something going on. Now, I can't prove that, oh, boys picked blue. I can't say that, but I can say there's a relationship here. Something strange going on. There's more differences than I expected just based on the proportions. Okay, so this is a chi-squared test. It's not super difficult to do. It takes some parts and pieces, of course, which, as we know, can be challenging at times, lots of parts and pieces. So to save us some time, I'm gonna use some technology. Technology is our friend. We just have to be able to use it. So we're going to try the same idea, but we're just going to write down the parts and pieces that we need to do by hand, and let technology do most of the testing for us. So we have hockey player Julie. She wondered whether the positions you played affected your likelihood of being injured. She went out and gathered some data. What position, what kind of injuries did you receive? And she created this table for us. So what should we be able to do by hand? So our by hand stuff. We need to write out our hypotheses. Part H, O. In this case, we're looking at her positions and their injury. So let's say position and injury, what do we want to call that? Severity, I guess, are independent. They have no relationship. Or alternatively, injury and position are not independent. And be careful, we don't want to use the word dependent. That's not necessarily the relationship we're establishing. We're just establishing that there is a relationship, not the kind of it. Okay, so I got to do that part by hand. The rest of this, figuring out the math part, we're going to use our calculators for. So our instructions. These are instructions right here. Let's move it over a little bit. We'll go through an example while we talk about this. Okay, so the first thing we have to do is enter our data. But to do that, we can't use our stat list anymore because we don't have a list of statistics. So instead, we're going to try this second x to the negative 1. It's the word matrix if you look on your calculator. Okay, so second x to the negative 1. I get a list of matrices. I want to edit A, so I can go over to edit and go into A. I now have to tell the graphing calculator how big is the table of data I want to use. And the order is rows by columns. So if we go up to our question for a second here, we have in this case 3 rows, so 1, 2, 3, and 3 columns. Okay. If it wasn't 3 by 3 and it was a different pattern, and you messed it up, it's not really a big deal. You can just always go back up to it and say, oh, it's supposed to be 3 by 4, or whatever it happens to be. Okay, we're going to type in the data that we have, the table of numbers. So we have 17, 24, 7, 18, 23, 11, 11 again, 13, and 7. Okay, check your numbers, make sure they're all right. And again, as I said, you can always go back up if you need to and change something if it was wrong. Mine look all right. Okay, so our data is in. What are we going to do next? Well, now we're going to do the test. So to do that, we have to go to Stat. That's then we're going to go all the way over to Tests. And we're going to find the chi-squared test. Now you can go all the way down the list, but it's actually faster to go up because the chi-squared test is at the very bottom. Letter C here. Chi-squared test. I want the fancy X. Notice that there is a C and a D that both have a chi-squared symbol. Make sure you're using just the chi-squared test, not the Goff one. We'll go into it, and we'll go down to calculate. Okay, just before I press enter, notice that I have 2 matrices. The observed one is an A. The calculator is going to keep the expected one for me in B in case I ever needed it. Okay, but it's going to do all those calculations for us. Okay, chi-squared test. Chi-squared is 1.14. So, let's write that down here. My chi-squared is 1.14. You might have noticed underneath that it actually tells you your degrees of freedom too, in case you forgot how to do that. Okay, but it gives it to us. So part C, degrees of freedom, it told us it was 4. And I need that so I can look at my chi-squared table. In my table, I'm looking at 4 degrees of freedom at 5%. I'll go back for a second to the table. Too far. 5%, so that's this one again. 4 degrees of freedom, that's this one. My number is 9.488, my critical value. I'm going to write that down over here. Critical value of 9.488. So what does that mean? Part D, let's make our conclusion. So how does this work? We're going to say since chi-squared, we're going to compare it to our critical value. So chi-squared was 1, critical value was 9. Chi-squared is way less than critical value. That means there's not that much difference. We have to accept HO. And the words we're going to use is there is evidence to suggest that the variables we picked, which were injury, severity, and position, are independent. They are not related. It doesn't seem to matter which position you play, how seriously you get injured. They are not related to each other. Okay, there's chi-square testing, at least the first part of it. There's more to do this. We'll look at that tomorrow. The homework is on the website. Just 2 little questions in the back of that handout. Answers there. Try them out. You can use technology. I showed you by hand so we know where it comes from, but I'm okay with us using technology to do the process.